Hey there, so this is going to be a pretty long video. So the first 7 minutes once it starts is going to be the overview of the build, and then everything after that will go a bit more in depth into how I do everything. And then finally, if you want to skip to the end, I'm going to be talking about how I'm going to make my next video about a 3D printing your bridge for your cello. So I hope you enjoy. Hello, this is Jared from Uncontained Curiosity, and I'm going to be talking about how I made this in a little bit more than a week. This video is not going to really focus on the design, whereas I'm going to really talk about all the hurdles I ran into, how I had to plan it, and some of the things that do relate to the design in the sense of, you know, what kind of tools I had to use and 3D printing parts and the kind of knowledge behind that. So the first thing that I had to do and plan out was the material selection and where to get it. So with this all being steel, I went right for a local recycling place that is also a supplier to some of these industries around in my location. They have a variety of just trash and recycled metal laying around where you can select it and get it by weight, have it weighed there, and then you get what you find in the yard. They'll have it pretty organized by like stainless, 304, 316, or you can get just some carbon steel, sheet metal, or anything really, and they have it organized and they're going to be the expert. So go in with a plan, know what materials that you want. So I know I just wanted normal carbon steel, not stainless or anything, and they come in 4x8 foot sheets. I got some 16 gauge that I had for another project that you'll see on the channel in the future, and I was torn in between 18 and 20 gauge, and so I ended up going with the 20, and I'm really glad I did due to the weight, and the parts that are here on the face and the side are all 20 gauge as opposed to what could have been 18. And to put in perspective of the price, a 4x8 foot sheet of carbon steel, whether it's 16 gauge or 20 gauge, range from about $60 to $80, depending on the gauge and just like the merit market. That's something to expect. There is really all the sheet metal involved here probably ran me a total of $100, $120. So I had some parts down here that I needed to get some 1-inch pipe. And it actually came from what used to be like an old strut or something. That's that first thing. So then going into the material even more, I needed the other parts like the, I just went for these kind of bass style tuners. So there's these kind of tuners that are like really tiny and they're for bass, but they look like a glorified guitar tuner, just a little bit bigger. And I didn't really think that would fit the aesthetic. And then if you look at like a contrabass tuner, they're like this, but like way bigger, but I like the look. So I know that they had this for like a P bass, like a jazz bass. So that's what I found, and I thought that, that would be perfect for the size, and it turned out really well in my opinion. So tuners, the steel, now we're looking at about $150. And then the strings, these are Diodario Pro Arte. They used to be Perlon core, but I think they changed it because they used to have some problems. The A string kept breaking and unwinding, and it was just overall a really bad experience. But they changed to a nylon core, and actually, so far I've been really surprised with the strings. They sound just as good as the Perlon, quote unquote, but they're just like a nylon core string. Those ran about $70 to $100 depending where you get it. I think I got mine for like $79 on Amazon, free shipping. Besides that, I had this old bass string from, I have a 5-string bass here. This is a low B or the low E, and I chose that to support these because if you look at the cello strings and their range and the tension that they run, the total tension of this is 100 pounds. And since there's going to be 2 runs, that's about 50 pounds per run here, and I know that those lower bass strings can support up to the 50-pound tension. So then we get to the 3D printing. So the 3D printing was a little bit challenging, where I had to I had to get the printer itself. You got the materials and setup for that. It's a relatively cheap 3D printer, and I'll post a link in the description for what it was. And a lot of time had to go into making that work because, to be perfectly honest, the cheap 3D printers are not like plug and play. You gotta kind of mess around with them and make them work. So that, and then the filament's about $20 per 1 kilogram, 1 point whatever kilograms that they come with of filament, and that'll get you a good amount of parts. So then, because it's steel, the welding is the other thing. Of course, that's, this wouldn't be here if I didn't have a welder. I have a Hobart Handler 190. I was running flux core line. I didn't have the investment to run like gas and like a proper wire and all that. So I think flux core just kind of tied me over just fine. And overall, I thought that, this would definitely turn out perfectly okay for what I needed. And in my opinion, it did. Not the most beautiful weld in the world, but it got me where I needed. So the Hobart welder, this is where, your cost of your tools is, you can go with a cheaper welder from like Harbor Freight or online, spend like a couple $100 and you got something that'll work, and it'll tie you over for flux core welding. But then once you want to try anything else, you're going to want to step up. But so where I'm getting at is I think that I'm going to invest more into welding in the future. So that's why I got the Hobart 190, and overall it was just a great experience learning and using it, and lots of practice. So overall, that's where I am with the welder. With that all being there, that's the tuners, the 3D printing materials, steel, and some of the little parts here and there. Overall, I was able to just get it online, get it at a metals recycler location or a local supplier for industry. And then the final thing is just general tool selection and things that you can get at your own your own pace. These joints, like the 20 gauge, is a little difficult, especially with the flex core. And then what was really difficult was the 16 to 20, getting those weld good, because you got to put more heat into the 16 gauge, but then the 20 gauge doesn't want to work well with it. So you just got to change your technique a little bit, and honestly, you just got to have a lot of raw material. So fortunately, I was able to find some locations that get scrap metal that I could just get for free because they'll just throw it out. So you can look out for local industries that have, they work with reservoirs, or they work with large structures or small structures where they're going to have a lot of waste material that they're just going to throw out otherwise. They don't really want to waste time with recycling or reusing it. That's why they'll send it to the recycling location that I went to. Or if you have a direct connection to it, then you can get some of that waste material for free, or just kind of having that connection. They're going to throw it out anyway. Final thing is, generally all the cleanup and overall the how to approach the finishing. So cutting and all those tools, I needed a grinder, I had a variable polisher, and then a whole bunch of flat wheels, discs, and drill bits, all these little things that you need to have that, you don't want to be caught in between not having the tool for the jobs. Because when I approach this, now you got to plan out your timeline. So starting that weekend, I took that whole week off of work. So the weekend, that whole week, and the next weekend, I had pretty much the full, actually 7 days, and then 2 more working for me. So a little bit more than a week. And then the following week, I would kind of dabble with some adjustments after I got it playing. Unfortunately, I didn't really take a lot of video of the build, so I'm just going to kind of commentary on each part of it here. Planning out all the cuts to the faces. I didn't have a bandsaw, so a lot of this was cut with a grinder. So with knowing that and all the curves and such, I left myself some extra material to cut away or weld away later. I found that when welding this 20 gauge with the flux core, it would actually, I would utilize the material that was overhanging as a buffer for the heat. With just cutting it with a grinder, I drew everything out with some Sharpies, and then I took some paper and I made templates so I could mirror the image across the axis. The design and all the mathematics behind it I'll get into in another video, but the point is I used a caliper and a few equations to follow while making some of these curves. And I used the caliper to, get those pretty well positioned, and then I used the paper template to make sure that it was symmetrical on each side. Once I got past the cuts, then it was the face. So the face has a slight curve to it, and I needed that for, I'll go more into the other video, but basically it needed to be both structural and it needed to be able to support the sound I needed in a particular way. So I don't want to get too in depth with it now, but the point is it needed to satisfy those two main points, being structural and sounding good. So the curved face was imperative to having that happen. So how I did that is I took actually a 45 ounce dead blow and a couple hammers, and I laid it on the ground and I just hammered away, and it started to, you'll see in the pictures, kind of potato chip up. And so as you hammer the back, when you hit the material into the ground, it wants to potato chip towards you. And then all this edging right here, it took a little finishing hammer, kind of like for putting in brad nails or just for furniture, little hammer, and I just hammered away at the edges. And what that did is it took the potato chip and it kept the curve in the center, and then it did this little flare on the edging. So I repeated that process probably like 2 or 3 times, and I got like a really good, here's the before and after, a really good, nice smooth finish, and overall I was really happy with it. Now later on, if I were to do this again, I think I would have put in a little more extreme curve, a little more pronounced, because some of the things I added here, some of the features I added to the body, and also overall welding it together, kind of took that and put it, it wanted to naturally go back to that flat state. So when you heat up metal and you weld on it, and when you are, working it overall and you're trying to get it to do things, it actually changes its internal structure. Or when I was hammering it, it was yielding and actually stretching and doing some other things. But then when I welded, through thermal expansion and the crystal structural changes internally, you have all this distortion that occurs. So you can actually see here at some of these points where the curves get really intense, that the face starts to like contort, and really extreme changes in the face that, to be perfectly honest, because I didn't work a lot with metal before, I just kind of I had to deal with as it came up. You definitely want to practice your welding, and overall that's something to expect, is that distortion when you, even though I had a really nice finished product when I was hammering it out and I got it to a look that I liked, once I started working with it further, it went downhill. So I had to kind of react and make changes as I was going. So that definitely increased the build time, and it was just a learning experience. To start here, I basically started at each one of these points, and I took the width of this, and I essentially started at one place, kind of measured out the circumference with a string, and then took that length, add a little bit more, and then I would just kind of tack weld it around, kind of keep going, bending it and, you know, hammering it in as I went. And then once I got some good tack welds in and I got it to each of the edges, I did the final weld and I went all the way around. And so I pretty much repeated that process for for the top half, and then for the bottom half I did the same process. So overall that went really smoothly, and you know, laying down some good tacks, getting the length right and hammering it in definitely was not a big deal. Where the difficulty got really hard, really fast is the neck. So I had my cello, my normal cello here, as a reference, and the reason why is since I scaled this up by 6% overall, I needed to keep the main dimensions with that 6% bigger, that fraction, on all the primary points from the nut to the bridge to this location, the tailpiece. Because if I didn't do that, it would throw off some certain things like that would make playability not any good. And so, for example, you know, just a little thing, when you play fourth position, you have your thumb here, and you kind of, on a good, you know, well-made wood cello, this is generally this little curve right here is going to be right below that fourth position, you know, the next string up. So I need to make sure that that was going to be in the right location, and that's by keeping those fractions all the same and looking at all that. I definitely needed to make sure that there was no deviation from that. So keeping that consistent, I was very careful in all the cuts. And what I did, and now this is, when you do like sheet metal work and you start out with the parts, you actually are inevitably starting out with flat metal, and then you have to hammer it out and bend it, or overall it's the final shape is derived from a flat surface. So there's actually, if you're to just look at one half of this, there's 1, 2, 3 pieces that make up just the sides, and then there's the fourth and the fifth part here that cover the remaining bits for just the neck. So how I made these parts is I took, this is all 16 gauge, I took the primary measurements of, you know, here to here and then here to here in overall length. So I pretty much laid out all the lengths throughout, and then I made my cuts where it was, and of course minding the 6% bigger. So this part kind of looked like you had this rectangle up here, and then what wrapped around actually had a channel that came out to about here. But because I needed this to wrap around, I actually brought the cut down all the way to about here, and then it wraps around. So it needed to be this length here needed to be the maximum height of this profile after it was bent. So even if you look at this part, this started as a flat surface that would have been the circumference, where the width would have been the circumference from this midpoint to the side, because this was all made in halves. I did not do the full section. That would have been a mess. So taking that, I had to consider the bend and also the cuts. So once I did that, I took some pipes, a couple vice grips, pliers basically, and I either hand bent it or I kept it in one of the vice grips, and then with my dead blow or the hammer depending on what kind of bends I needed, I pretty much was just pounding away on some pipe, and also an old concrete block that I had that was, you know, as I was hitting at it, it was just enough give to like break away, but also it left some nice curves on the concrete block to, you know, allow some natural curvature as opposed to getting all these little kinks in it. And that was really nice for the most part. So overall, pounding away on each of these and making sure all the measurements were good took the longest time. And then again, I left some extra material, and then when there was too much, I cut it away. So then I just went and did the same thing for the fingerboard. That was a little bit easier because it's 20 gauge. I mean, I could literally just bend it with my hands at some point. So really, I bent it out and then I would hammer it into place because, you know, when you do a natural bend, again, with the whole thermo expansion when you weld and all that, I needed to get some good hammering into there because that actually yields the metal a bit more and actually adds some internal stresses that are preferable over just like doing a bend overall. So that hammering actually, you know, changed the internal stresses with the surface itself. Even though it's really thin, it still made a really big difference. So overall, this curve was derived from my normal cello, but because I knew I wanted this to be a bit bigger, I knew that this space versus, like the spacing of this versus where the strings are in comparison to each other, I didn't need as much as an extreme curve for the bow not to hit when you're bowing. So knowing that, I kind of had a more shallow curve, and overall this is a much bulkier neck, so I didn't want like a really intense curve and a bulky neck. So overall, that was just kind of a personal design thing that I wanted to try, and overall I like the feel of it. So going further with that, this was the hard part where I took the 20 gauge fingerboard, and then this is where, you know, this is it. Well, in the 20 gauge, the 16 gauge neck was the most nerve-wracking part ever, because as I was doing it, this part of the fingerboard that I, you know, had a nice curve to started to flatten out in some places, and it was, you know, I'll post a picture here, but overall it was just really messy, and I really wish that it wasn't so difficult, but it was. And then I have a 16 gauge support here for the bottom, and this didn't really need a lot of structure because when you look at the cross section of this with the curve and with the flat piece there on the bottom, I increased what's called the moment of inertia for it with having that curve. So it pretty much provides its own natural support, and also it has like a nice scoop to it that I could adjust later. And if you're not familiar with the term, the scoop is the distance. If you're to take this string and run it down, this point will be close to the string, the midpoint will be a little bit farther away, and then the nut will be, you know, really close too. But the point is if you're to lay at something perfectly flat, such as the string, you'll see a small point in between here, and that's called the scoop. And so all cellos have a natural scoop to them, and I needed to make sure that that was part of it, and it affects playability again. So once I got to that point, this is just where I kind of got a little more artistic. The head I did with, I took some paper and I took a few measurements and I drew out a few designs. But the thing that I found in my experience that's hard with headstocks is they could just be awkward if you get in the wrong size and the wrong proportions. They won't look right. So I had a few iterations that I worked out, and I also did a direct comparison to my wood cello to make sure that, you know, this was going to be in the right place and where this was going to be. Because something that I learned that was really interesting while I was making that is that you might not realize it, but the nut is actually just about perfectly in plane with the body. From the bottom to the top to the nut, you can pretty much draw a plane there, and then if you're to continue that plane further, it hits the top of the headstock. So it's not that the headstock is cocked back, but rather it's actually got this really pronounced curve to it that comes back. So that's something I didn't really realize. I never looked at it. Just, you know, you saw the scroll in it, you know, it's a scroll, but in the actual design, when I realized all this was in plane and stuff, you know, that really helped with, you know, planning out this and all these other parts to make sure that this didn't look awkward. Because that was the thing that I was most worried about is, you know, besides the playability, I didn't want like a really awkward headstock that, you know, the strings couldn't go in there and you couldn't tune it. And overall, I was really careful with that.
So the absolute final thing I had to do was fit these tuners here into the headstock. I had to modify one of the ones near the top, as you can see. It's a little bit shorter, and then I also had some drill some holes through the actual post that the strings wrap around. And then finally, after all that, was the 3D printing of the bridge and the design of that. But since I'm going to do an entire video on 3D printing a bridge for your cello, I figure I'll just talk about it in that. And I really, really appreciate you guys sticking around and listening to the whole thing. And have a good one.